Thank you very much for the invitation for this very nice workshop. So in this talk, I would like to focus on quantum impurities that are immersed into a many-body quantum bath. And the problem dates back to Lev Landau, who studied the mobility of free electrons that are interacting with phonons in the electric crystals. And another very famous impurity effect is the Kondo effect, in which immobile spin impurities gives rise to enhanced resistance in metals below the Kondo temperature. And so these are famous impurity problems. And recently, with advancement in technology and experiments with ultra-cold atomic gases, it's now possible to study impurities that are immersed into ultra-cold atomic gases. And also recently, there were experiments in which impurity physics was discovered with semiconductors, this quantum impurity physics. And semiconductors are open quantum systems, especially at low temperatures. So there's a need for a development of formalism that will include coherent formation of quasi-particles and driven-dissipation on equal footing. And we work on such a theory, and here I would like to present some results on non-equilibrium properties of Fermi polarons. What are polarons? I will discuss in a moment. So here's the outline. First, I will describe the background and motivation for studying polarons. Then I will describe the theoretical tools that are used in the fields. And then I will describe Fermi polarons in 2D systems, where we found an interesting effect, which we called laser, polaron lasing. And eventually, I will talk about the driven Fermi polarons in 3D. So the concept of the polarons emerged in condensed matter physics to describe electrons moving through the electric crystals. And as a result of this movement of the electron, the impurity, which is electron, displaces the ions from equilibrium positions. So this can be understood as a cloud of phonons that surrounds the electrons. And this increases its effective mass and decreases the mobility. So Landau was the first one who studied this problem and coined the term polaron. Later on, Feynman and Frulich developed their models and approaches, like Feynman path integral approach, which was the most fruitful. And now we understand quantum impurities in a more general case, that these are quantum impurities that can be interacting not necessarily weakly with quantum environment, like atomic physics or electrons in a semiconductor. And depending on the statistics of environment, we call them Fermi polarons, if they are in a fermionic path, or both polarons if in the bosonic. But I will here focus on the Fermi polarons. And such quantum systems with impurities allow for the study of quasi-particles formation, control of the dynamics of quasi-particles, probe of the correlations of the environment, and also study the phase diagram for finite density of the impurities. So with the developments with ultra-cold atomic gases, the signatures of Fermi polaron physics were observed. And there are two general schemes to attack this problem. One is to use either a mixture of different species, or to use a single species, but with two different hyperfine states that can be independently addressed. And polaron physics shows up as in the spectrum of impurities as sharp resonances in the spectrum of the impurities. And crucial here is the possibility to tune the interaction with the technique called Feshbach resonances. And I will just briefly mention that there is a separate area of research that includes the both polarons. And also recently they started to investigate experimentally non-equilibrium approach to the impurity physics. And as a different different platform for studying polarons is based on semiconductor physics. Now these are 2D materials, especially these two transition metal dechalcogenides. They host exceptionally bound excitons, and we can treat them in the first approximation as without having any internal structure. And such experiments with excitons were performed in Atac-Imamoglu's group. So here the impurities are optically excited excitons, and the environment is formed by the doping of electrons. And they can tune the density of this mixture. So they observed also the signature of polaron physics. So here's the energy, here's the density, here's the energy. So they found that the impurities can have two states, and they call the one repulsive polaron and one is the attractive polaron, because one has the lower energy. And they also studied the interaction between the polarons and showed that the interaction is much stronger. So these platforms are quite nice because they have the possibility to do pump probe experiments, to tune the density, and also to strongly couple to light. But the cost is that the excitons are very short-lived particles, so they need to be repumped. So these systems are inherently driven-dissipative in nature. So to start, how to describe the polarons theoretically. So here's the Hamiltonian that consists of the environment, the impurities, and the interaction, which we take in the simplest approximation as the contact interaction. And the basic tool in the field is the Chevy ansatz. So it's an impurity times the Fermi C, or the impurity, one impurity and particle Hall excitation on top of the Fermi C. So we plug this into the mean value of the Hamiltonian, do the minimization, and calculate the dispersion relation as a function of momentum. And this gives also the effective mass of the polaron. The other tool is based on quantum field theory in equilibrium. So this approach is based on calculating green functions, and green functions are expressed in terms of self-energies, and self-energies are expressed in terms of T matrix, and T matrix is expressed in terms of T matrix and interaction and green functions. So from these, we obtain that there are two branches of the attractive polaron, as shown in these spectral functions, and the higher energy state is the repulsive polaron. And this approach for this state gives exactly the same results as the Chevy ansatz. But here, in this approach, we assume that the system is either in isolation, so we can use the wave function in the ground state, or we have the system that is in equilibrium. So there is a need to go beyond this limit and to develop a theory for non-equilibrium states. So we worked on such a theory, and we based our consideration on non-equilibrium quantum field theory, which is a generalization of Matsubara theory, and it's based on Keldysh approach, and it includes all the drive dissipation and interactions on equal footing. Here's the review of the theory. So we start from the partition function in terms of the field integrals. We have impurities, environment, and interaction, but now we have the green functions in the form of the matrices. So we have the retarded and advanced green functions. They also show up in Matsubara field theory. But now, since we don't have the thermal occupation, we need an additional object that carries the information about occupations of excitations in the system. And this is given by this Keldysh component. So in terms of the operators, we can write also the Keldysh and green function in terms of operators. These are either commutator or anti-commutator for different space-time points. So in our theory, we include this kind of diagram that we have an environment particle interacting with the impurity and forming a molecule. And this is known that this process has to be taken into account to get agreement with Chevy ansatz and meaningful results. So these are the self-energies, if somebody would like to know, that we take into account. So here's the impurity, the molecule, which carries two particles, and the environment particles. So if we have self-energies, we can calculate the spectral function of the impurities, and it's given in here in 2D. So this is the attractive polaron. Here's the energy, here's the momentum, here's the repulsive branch. And we also have the kinetic equation. So this is the equation for the Keldysh component in this form, but with some approximations called Wigner approximation, we can arrive at a simpler form, which is given by a kinetic equation with loss, pump, and collision integral, which are expressed in terms of the transition rates, and the transition rates are expressed in terms of molecular green functions. So we apply the formalism to semiconductors with excitons and photons, and that are immersed into electrons, and to the following scheme. We have the pump here that pump the higher energy branch, which is the repulsive polaron here. So the coupling to excitons, the coupling of excitons and the polarons is only to photons, is only here. So the photons can emerge only in this very small window of momenta. But if we pump the impurities here, they can excite to the lower branch and eventually accumulate here or be lost through the radiative emission of photons. So we take some energy scales here, and mass of the exciton is 2 times the electron mass, because it's a electron hole mount state. And the total density of impurities looks like this. So for weak drive, we have exponential relaxation to the steady state, but for strong drive, we have the density first overshoots and then relaxes. So this is compared to the case when we neglect the coupling to photons, which are these dashed lines. So for stronger pumps, we need the non-radiative decay and coupling to photons. So here's the total density. So it shows that for weak drive, we have a broad distribution, and for strong drive, we have a peak is emerging at small momenta at the tail of the loss profile due to the coupling to photons. So this is important that we have this peak at the distribution. And this peak shows up also in the emission of the photons, because it's related to radiative decay. So we measure the total number of photons, and we see that for small pumps, weak pumps, we have a linear scaling, but with smaller efficiency, radiative efficiency, and for larger pumps, we have this non-linear scaling with higher radiative efficiency. And this nonlinear dependence shows up also in this emergence of the peak at small momenta in the coherence of polarons. So we calculated the coherence, and for weak pumps, we have a rapid drop of coherence, and for strong pumps, we have oscillations and a much weaker decay. The width is about 20 times larger. So we have a threshold in the emission and long-range coherence. So we also calculated the momentum peak from which we emit the photons, and there is a jump. And we analytically predicted that there is a scaling with this funny exponent here, and also the distribution of polarons at larger pumps also follows this scaling. And also the spectrum of the emitted light has around the threshold decreases. But what is interesting here is that the width of the spectral function, measured here by the full width at half maximum, is below the non-radiative decay rate of the exciton here. And this is due to the fact that polaron is a composite object, and some of the excitation, a part of the excitation, is stored in the medium. So we can go below this limit. So we have an emission at finite momentum, and we have extended temporal coherence. Now, we also tested our theory for in a different case. There was an experiment in Sesto Fiorentino with ultracold atoms. So they have lithium fermionic atoms, but now they have three states. One state is occupied, one is strongly interacting, so we have polaron physics, and we derive the polaron states with a non-interacting third state. So they did that experiment, and we wanted to describe this with this quantum field theory non-equilibrium approach. So the Hamiltonian is like this. It includes this coherent drive with some detuning. We generalized the theory to include this term. Also now these become matrices, so matrix of matrices. And we derive the kinetic equations in which there are coherent transitions, and we have collision integral and the coherence. So interesting is that these quantities, kinetic equations support some modes with frequencies, and these frequencies scale with the square root of the quasi-particle residue. And this is confirmed by the experiments that this scaling holds. Also, these equations separate between relaxation with this collision integral and the coherence due to the interaction with the bath of the polaron. So they measure the total number of atoms in each hyperfine state and plot this quantity. So when the driving field is on resonance with the attractive and repulsive branch, where they see the oscillations, and these are calculated for different values of the interaction strength between the atoms. So this is an interesting point because it's the unitary limit in which the interactions are infinite in some sense. So the scattering length, which describes in the ultracold limit the interaction between atoms, is infinite. So we also analyzed how the system thermalizes by developing an estimated temperature based on Kullback-Leibler divergence. It's a concept from quantum information theory. And it turns out that the system is quite far from the true temperature, which is here. So we really need a non-equilibrium approach to these quasi-particles. And also, an interesting thing is that even though the interactions are extremely strong in this limit, they observe the oscillations and the coherence of the polarons. And this work was done in collaboration with Francesco Piazza from Max Planck Institute in Dresden when I was a postdoc, with Falco Piętka from Frankfurt, Johannes Lang, who now is in Cologne, and Alessio Recati and Matteo Stiginolfi from University in Trento. So to conclude, I told you about Fermi polarons in non-equilibrium systems, why it's interesting and why we need non-equilibrium theory. And I applied the theory to two cases. One is the semiconductors, when the atoms are weakly coupled to photons, and we observe the effect that I called lasing. And I told you about the coherence and relaxation of Fermi polarons with atomic physics. Yes, oh, sorry, thank you.
Thank you very much.